right now, I mean, somewhere out there, there is this hyper-advanced data center.
Oh,
And it's, generating the most brilliant poetry or complex code we've ever seen.
yeah, the kind of medical research that feels like absolute magic.
Exactly. It feels like a total miracle of the digital cloud, right?
Yeah.
Like it's weightless,
Yeah.
invisible, frictionless. But then, sitting right next to that exact same pristine data center
Mm.
is this massive, incredibly loud, totally unglamorous industrial cooling tower.
And it's just drinking millions of gallons of local municipal water.
Right. Millions of gallons. Which brings us to our mission for you today. Welcome to the deep dive. Today, we are pulling apart a stack of sources that, well, they completely reframe how we should be looking at the future of technology.
They really do.
We're looking at the GOA-44 thesis, which is this fascinating strategic assessment of global resource allocation, along with two highly analytical frameworks known as the LMOS and MCP models. And our goal today is to figure out why a purely information-based revolution is suddenly obsessing over pouring thousands of tons of concrete and laying miles of high-voltage copper wire.
It's the defining paradox of our current technological era. What we are exploring today isn't really a debate about which AI algorithm is the smartest.
Right, we're zooming way out.
Exactly. We are looking at a massive structural observation. The expansion of artificial intelligence is pulling the world's attention quite violently, actually, back to physical constraints.
Because we all thought we were observing a software revolution.
Yeah, we did. But if you look at the data in these sources, we're actually watching electricity become the central variable of human civilization once again.
I think anyone who follows tech closely already knows that, AI uses a lot of power.
Right.
We've all seen the headlines about data centers straining grids.
Sure, yeah.
But the GOA-44 thesis treats this not just as a logistical hurdle, it treats it as a total paradigm shift. And I want to move past the basic, like, AI takes electricity idea, because it feels like the sources are pointing to something much deeper.
They
We're
are.
talking about thermodynamics.
That is the absolute core of the GOA-44 thesis. The document essentially argues that we need to stop thinking about AI as software entirely.
Oh, wow. Stop thinking about it as software.
Yeah, and start thinking about it as heavy industry. A
Yeah.
traditional cloud server, the kind that hosts a website or an email database, might draw, say, 5 to 10 kilowatts of power per rack.
Okay, 5 to 10.
But a high-density AI server rack packed with all the latest GPUs doing intense mathematical training, that can pull 40 to 100 kilowatts.
Wait, really? 100 kilowatts for one rack?
For one rack.
Yeah.
And when you pull that much electricity into a tiny physical space, the laws of thermodynamics dictate that almost all of it turns into heat.
Oh, because computation is essentially just organized electrical resistance.
Exactly.
So the data center isn't just a brain, it's a giant space heater.
A massive one.
And that explains the giant cooling towers I was talking about. The water is just acting as a thermal sponge to pull all that heat away from the silicon before it literally melts.
The physical infrastructure required to manage that heat is staggering. The GOA-44 thesis points out that as these models scale up, the competition isn't just for the most training data anymore.
Like it used to be.
Right. Now it is a brutal physical competition for industrial-grade cooling equipment, for access to massive freshwater aquifers, for robust power grids.
So AI is taking the background elements of civilization like public utilities, water rights, municipal power distribution, and forcing them right to the forefront.
Yes, they are becoming critical strategic assets for national security and global financial markets.
Which brings us to this fascinating concept in the sources, the velocity mismatch. Because my immediate thought is, if an AI company just pays for the infrastructure, why can't the physical world just, hire more people, pour more concrete, and speed up?
It's a natural question.
Right, like, is this a regulatory bottleneck or a literal laws of physics bottleneck? Because I'm looking at the LMOS framework here, which stands for Local Macro Operational Sync, and seems to suggest the system is actually tearing itself apart trying to keep up.
Well, the LMOS framework gives us a way to measure the friction between different systems. And you hit on the exact mechanism causing it. Time. Yeah. They measure this friction using a concept called shear. Shear happens when two interconnected systems operate on fundamentally different timescales. Think about how an AI company operates.
Okay.
They function at what the models call OS speed, or operating system speed. They can secure billions in funding, design a new server architecture, and order tens of thousands of GPUs in, like, a matter of months.
Right, their expansion cycle is measured in quarters, sometimes weeks.
Exactly.
But the physical grid moves at, what, century speed? I was visualizing this earlier as a massive operating system compatibility error.
I like that analogy.
It's like trying to drop a hyper-advanced Formula One racing engine, which is the AI demand, into a heavy, rusted farm tractor, which is our physical electrical grid.
Right.
The F1 engine wants to go 200 miles an hour immediately, but the tractor's transmission physically cannot spin that fast. If you floor it, the engine doesn't make the tractor go faster. It just shreds the gearbox.
That is exactly what's happening. In the LMS framework, they measure this friction directly by looking at the timelines for infrastructure development. A tech giant can build the shell of a data center in a year.
Okay, 1 year.
But to power it, they need a high-voltage transformer. Right now, the global supply chain backlog for a custom high-voltage transformer is often 24 to 36 months.
3 years just for the transformer.
Yes. And if that data center requires a new transmission line to bring power from a distant wind farm or nuclear plant, running a high-voltage line across a single state takes time.
Because of what permits?
Navigating the environmental reviews, the local zoning laws, the right-of-way negotiations, that takes 7 to 10 years, sometimes 15.
So that friction you mentioned is the gap between a 6-month software deployment cycle and a 10-year concrete and copper deployment cycle.
And that gap is where the global system is starting to break down. We have a global phenomenon where the computational desire of the digital world is essentially infinite, but the electrical reality of the physical world is strictly capped by the speed of heavy construction.
This velocity mismatch explains the friction perfectly. But friction creates heat. If the grid is tearing itself apart trying to keep up with the data center, that heat has to dissipate somewhere.
Exactly.
But what's weird to me is how quiet this all feels. I mean, why isn't this dominating every single headline? Everyone is loudly debating AI stock prices or arguing about whether a chatbot is sentient, but nobody is talking about the transmission cables or this supply chain for transformers.
Well, the sources actually have a term for that exact phenomenon.
Really?
Yeah, the LMS models use a concept called silence detection. Major structural shifts in human civilization almost always begin quietly. The world doesn't usually change in the loud, noisy places of public debate. It changes in the silent, foundational layers. While the media focuses intensely on the software layer, like the user interface, the prompt, the output, the actual tectonic shifts are happening in the physical background.
It makes sense, I guess.
Yeah.
We are conditioned to look at the screen, not the power outlet.
Right.
But if these changes are invisible, or at least, operating beneath the surface of the daily news cycle, how do we know they are actually happening? Where do we look to see this structural shift?
You look for what the framework calls tension membranes.
Tension membranes, like in biology.
Just like biology. It's the boundary where two different environments meet. You spot the structural tension right at that contact point.
So where is that happening right now?
For example, we are seeing fierce scrambles behind closed doors for grid connection rights. In some major tech hubs, the queue just to get a feasibility study for connecting a new data center to the regional grid is now 5 years long.
Great, 5 years just to get a study on whether you can plug in.
Just for the study.
That is incredible.
We are also seeing a sudden, urgent reassessment of baseload power. Tech companies are actively looking at funding next-generation nuclear reactors or securing long-term contracts with liquid natural gas facilities.
Just to guarantee the power.
Because intermittent sources like wind and solar simply cannot guarantee the 247 uninterrupted megawatt flow that an AI training cluster requires.
Right. The servers can't take a break when the wind stops blowing.
Exactly. The real revolution isn't loud at all. It is the quiet, invisible rewiring of physical resource allocation across the globe.
And looking at the sources, it seems like that tension at the membrane eventually leaks into local neighborhoods. Which brings up an incredibly important question for you, the listener, about who actually feels the impact when the bill comes due.
That's the real issue.
Because the data center doesn't exist in a vacuum. It exists in a town. It exists in a county.
And the documents draw a very sharp contrast here between two entirely different realities. From the perspective of a global tech corporation, or a nation-state trying to maintain its geopolitical edge, or an investor looking for returns, securing massive amounts of power for AI is a globally optimized decision.
It makes total sense for them.
It is perfectly rational. It makes complete mathematical sense on a global spreadsheet to build the biggest facility possible.
But the mathematical logic of the network doesn't map cleanly onto the physical reality of the town. It's like the ultimate civilizational NMBY issue. Not in my backyard, but on a completely unprecedented scale.
Absolutely.
Because the benefits of AI, like a smarter chatbot or an algorithm that optimizes global shipping, are distributed globally. Anyone with a smartphone gets to experience the magic.
No.
But the costs of generating that magic are intensely, painfully hyper-local.
You see this collision most clearly in resource management. The global digital operating system makes calculations that are mathematically optimal, but those decisions create severe, tangible friction when they touch down in the physical living environments of local populations.
Right.
The algorithm optimizing a data center's cooling protocol doesn't factor in the local water pressure or the region's long-term drought conditions. It only calculates the flow rate required to keep the GPU temperature below a critical threshold.
So you end up with situations where a single facility might be drawing millions of gallons of potable water a day from a local municipality,
Yeah.
putting massive strain on the local water table.
Exactly.
Or, going back to the electricity side, local utility rates spike for regular families because the regional grid has to spend billions upgrading its transmission lines just to handle the load of a new tech facility. The friction is absorbed by the local community.
And this brings us to the third major framework in your stack of sources, the membrane contact phase, or MCP model.
Right, the MCP models.
Because as this hyper-local friction increases, the natural instinct of engineers and policymakers is to try and solve it through absolute optimization.
Well, sure, the thought process is, if the digital world is demanding infinite speed and infinite power, and the physical world is too slow and messy, we just need to force the physical world to speed up.
Right. Remove the blockers.
We remove the regulatory friction, we streamline the supply chains, and we synchronize the tractor to the F1 engine by making the physical world hyper-efficient.
It is the most common technological impulse, but the MCP models provide a deeply counterintuitive warning about exactly that approach.
Yeah.
They argue that total synchronization and hyper-efficiency are actually incredibly dangerous for complex systems.
I really want to dig into this because it goes against everything we are taught about progress. Are the sources actually saying that inefficiency, things like delays, excess capacity, and administrative friction, is a good thing?
In a structural sense, yes. If you design a civilization's infrastructure to remove all friction and force everything to run at maximum synchronized efficiency, that system eventually loses its adaptability.
It gets brittle.
It becomes incredibly rigid. The MCP models call this a state of chronic depolarization.
Chronic depolarization.
Yeah.
That sounds medical.
It is borrowed from biology. A biological system running at maximum heart rate constantly, with zero rest, eventually suffers cascading organ failure.
Right.
In an electrical or logistical grid, chronic depolarization means a state of permanent exhaustion. Think of a regional power grid that is constantly running at 99% capacity just to keep up with the baseline digital demand day in and day out.
I see the danger there.
Yeah.
If you are constantly running at 99%, you have absolutely no buffer.
None. The models introduce the concept of liquid stability as the antidote to this.
Liquid stability.
Think of liquid stability like shock absorbers on a car. If you engineer a car's suspension to be perfectly rigid so that it transfers 100% of the engine's power directly to the wheels, removing all the quote-unquote inefficient flexibility, the very first pothole you hit at high speed will snap the axle.
Because the system has no way to absorb the kinetic energy of a surprise event.
Precisely. That is the point of the framework. In civilizational terms, that play in the system is excess power on the grid. It is water reserves in the reservoir. It is the time it takes to carefully review a construction permit.
It's the slack.
Yes. A healthy system needs margins of error, it needs redundancy, it needs what the models call fluctuation, basically a bit of noise and a bit of slack in the system.
So if we allocate every single available watt of power and every drop of cooling water to perfectly optimized AI data centers, we are essentially snapping the shock absorbers off the grid.
We are.
Which means a normal summer heat wave doesn't just cause a temporary brownout anymore. It causes cascading structural failures because the system has zero recovery capacity left.
The models argue that long-term care and stability require cognitive cooling and physical buffers. True health in a civilization isn't about moving as fast as possible without error. It is about the capacity to recover when the inevitable error occurs.
Right, because errors will always occur.
Always. And if the AI revolution forces the physical world to operate without these buffers, we risk creating a brittle, rigid system that is highly prone to catastrophic collapse rather than smooth adaptation. Total efficiency eliminates the system's ability to heal itself.
That reframes the entire concept of progress for me.
Ugh.
We spend so much time and energy trying to optimize our workflows, our cities, and our grids. We view any idle resource as wasted capital.
Exactly.
But if everything is perfectly optimized, a single snapped wire, an unexpected drought, or a spike in natural gas prices breaks the whole machine, we actually need the slack.
And when you scale that loss of slack up to a global level, the geopolitical implications are immense. The goal shouldn't be to force physical reality to match the breathless speed of the digital algorithm.
That's the trap.
Right. The goal, according to the MCP models, should be to deliberately maintain that liquid stability, a state where the system can flow, adapt, and recover from shocks. If we lose that in the pursuit of computational supremacy, we don't just get a slower internet connection, we get a chronically exhausted civilization.
This has been a fascinating journey through these frameworks. Let's try to pull all of this together, because the implications of GOA-44, the velocity mismatch, and this need for liquid stability really change the narrative of the next decade.
To bring the conversation full circle, the grand realization of this analysis is a fundamental rereading of our current era. The AI boom is not, as the marketing often suggests, the moment when human information finally becomes fully independent of the physical world.
It's not an escape into a weightless, frictionless digital utopia.
It is the exact opposite. It is the exact moment when our vast, infinite digital ambitions violently reconnect with hard physical reality. We spent decades abstracting our lives into the cloud, but the cloud has a physical footprint. And that footprint is made of concrete, copper, fresh water, and thousands of megawatts of electricity. We are not leaving the physical world behind. We are becoming more dependent on its fundamental constraints than ever before.
We've spent the last 20 years thinking we were transcending the physical world through our screens. But if the next era of civilization is dictated not by who writes the most elegant code, but by who controls the nuclear power plants, the municipal water rights, and the supply chains for high-voltage transformers, well, it completely flips the script on what power looks like in the 21st century.
It really does.
I want to leave you with a final thought today. I want you to look around your own community today. What quiet, quote-unquote, boring physical resource sitting right outside your window is about to become the most important strategic asset on Earth? Because whoever controls that controls the cloud. Catch you on the next Deep Dive.